Hi everyone, it's Rogerio. This week I made a presentation about DSPy in AI Builders meetup here in Amsterdam, and I tweeted out about it, and a couple folks asked me if there was a recording. There was none, and then they asked me like, hey, why don't you do a video about it? I'd watch it. So here we are. I'm going to go through the DSPy presentation. How is it that DSPy replaces some part that we humans currently have to do as AI engineers, and why this is such a cool, new, exciting framework. So first of all, on DSPy, some people call it DSPy, some people call it DSPy. Omar, the creator, calls it DSPy, but maybe it's like a GIF situation. It was created by Omar and a couple of other guys from Stanford, and it really is heavily inspired on PyTorch. Maybe you cannot see from my little video over here, but yeah, there is a PyTorch logo over there. But before we get into that, I want to talk a little bit about prompt engineering. So if you have been in the LLM game at all, you certainly notice that there are some strategies that you can do to make your prompt look better or work better for what you want. And a lot of people noticed that, and they started classifying it, organizing those techniques, and even doing lots of research and papers on it. Some actually have proven metrics on how it increases the LLM quality. For example, the few-shot prompt. The few-shot prompting is basically giving some examples to the LLM before it gives a response. So like, I want you to behave in this certain way, so here is some examples on how you should do it. Now you go. So you give those examples or demonstrations, and of course, obviously, being in like a predict next word machine, that totally makes sense, right? It's following patterns. If you give it a pattern, it makes it so much easier. And some others like chain of thought, that you say like, instead of giving me the answer directly, just think it through and then you give me the answer. Some of those became so popular because they're so powerful that they became integrated directly on, for example, ChatGPT or Claude. Like when you ask them something now, a lot of times they actually do a kind of chain of thought there. They think it through first before answering you, because that increases the quality so much. And there is all those different, let's say, strategies or structures or components that you can put around to increase your results. Probably the most popular one right now that everyone certainly heard about is the RAG, the Retrieval Augmented Generation, that if I give it some context that I have in my database, it can actually give way better answer, of course. However, first of all, you need to think of when to use each of those techniques and each point. And even if you do, it doesn't mean that you're going to use them the best way. All those techniques, they still require prompts, right? So if you wanted to give a few shot examples, you still need to say like, hey, I'm going to give you these examples and I want you to behave that way. Here are the examples. So you need to think on how the prompt will look like, the structure look like. If you want to do RAG, then you first do probably the retrieval step. You're like, yeah, from this that the user gave, generate me a query. And then after the results, you're like, okay, I retrieved those. Now answer the user original question. And how those are asked, and of course the content you put it in is so important and makes so much difference. And what we do is usually tune those by hand, right? Like you might retrieve one, you might switch one technique with another, but maybe you're not using the best of the technique because you didn't have the best prompt. And then your prompt is working, you might switch something, it stops working. If you switch models, then you have to throw all your prompts away. You need to like prompt engineer all over again. So just to represent a little bit on how is the work that we do right now, how does a RAG application work in summary? You basically have an input that is the user question, for example, and then from the user question you generate a query to be retrieved on the database, which is not necessarily the same as the question, because sometimes the user asks, the user asks a question about, I don't know, some actor, but in your vector database it will not be represented as questions but as facts. So you need to rewrite that to have better answers. And then you do the retrieval. Then after you do the retrieval, you take those answers that you got, you give it back to the LLM, and then say, yeah, please reply the user now that you have this added context, and then you get the output. Very simple, but if you think about it, who gives the input is a human. It's us. It's like if you're testing, if you build a RAG system and you want to test out if it's working, then you are going to do a query yourself, then you see the results and you're like, okay, that works. And I'm using Zuckerberg to represent the human there because he told us once that he was
But it is going to bother you because you're human, and I was human. I am human still. But I was just referring to myself in the past.
Sure, Zuckerberg. Yeah, we still believe that you're human. So yeah, let's continue. So let's say you go there and then you try it out. You ask a question. Then with your question, it needs to generate a query, right? And who wrote the prompt for generating this query? That was also you, the human. Then it does the retrieval on the database, and then it generates an answer, which is done by a prompt that you also wrote. And of course, the LLM, that was the one generated the query, and then the LLM also generated the response obeying the prompt that you typed. And who defined this overall architecture, how all those components are connected together? That was also yourself. And then you run this test, and then you check the answer, right? How good is it? If it works the way you expected, and who checks that? It's also you. So you are also the human doing the evaluation. And for the biggest part, this is how it goes. Like, this is how you prototype, this is how you build an LLM application. And if you are just testing a lot and then like looking at if it feels right, we call that vibe checking, right? You're checking for the vibes if it's right. You might be checking if it's specifically right, like if you have a golden answer, especially in the case of RAG, maybe you do have an answer to that. But a lot of times, you also just kind of feeling it, and then and then when you decide you're good enough, you put it live out there. Okay, but then what if we keep the LLM to generate the stuff, obviously, but what if instead of us validating by hand each generation that happens, what if we wrote some code that could validate that for us? And then not only that, what if instead of us trying examples hand by hand, if we just collected a set of examples, let's say you have like 100 examples that you wrote yourself, or maybe you ask a ChatGPT to generate examples for you, right? Like, I have an application about this, can you generate me 100 different examples? So you can put that in a CSV and have all those examples side by side or line by line. Then this alone allows us a very cool thing. It allows us to have an LLM writing prompt for us. How so? Well, now you have an automated way of evaluating. So you can run those examples in a loop, one by one, and then you see if it's correct or if it's not. And then if it's not correct, you can tell the LLM like, hey, this example didn't work out as I expected. Can you try to tune the prompt to make it better, to get better results? So now you can, instead of us writing the prompts ourselves, we can tell the LLM what the prompts are about, and it can validate itself, given the examples and give the evaluation code, and in both components, right? Both to generate the query and both to generate the answer. And then why not? We can have LLMs generate the input. Like I said, you can have those 10 examples you wrote by hand, then you expand it with ChatGPT or whatever. You can have it writing more and more examples for itself on things that it thinks that it can break, and then it improves the prompts. And then, why not? You can have also an LLM doing the validation on how good it is. You can have something doing the vibe check for you. And then what's left for you is to define the architecture. So this is the whole concept of DSPy. This is very similar to what they were inspired for from PyTorch, from machine learning world. If you think about it, machine learning was always about having a ton of examples and then having some way of validating, like if you're doing supervised learning, right? Or even when you're predicting next word for LLMs, it is also a validation. You have a way to score how correct that is. And then you can be just responsible for the architecture. You can look at those components and then like, what if I switch them around? Would it improve? So then you become just more meta. And this is basically the DSPy optimizer process. It takes an input and then it goes through a network, look at the response, does a validation on it, and check how wrong it is so that the optimizer can actually improve those LLM prompts, for example, or the demonstrations that it's giving it. And then you are in charge of just taking care of the architecture. And this is very, very similar to what happens in machine learning on neural networks. This is what it took us this far, right? With GPT-4 and everything. So you have a data set, usually a huge data set, you have all those neurons, and then you have some validation with an optimization process, which we call training, that keeps tuning those weights. And we don't look at the neural network and then we go on those weights like, what if I switch this a number up or a number down? We don't do that. We're mostly worrying ourselves about the architecture. Should I use LSTMs, RNNs, or transformers now? And similarly, DSPy brings the idea that maybe we shouldn't be tuning those prompts by hand. Maybe we can define this architecture and let the machine find the best prompts for it, for exploring that architecture to its maximum potential, let's say. So if we were to put those two side by side, what we call model in machine learning, we call program in DSPy, because those are components block and you have an LLM program running. In machine learning, what we call training, in DSPy we call optimizing. So while you train your model, you optimize your program. And then the output of this training on a machine learning model are the weights. So what you call model is actually the stored weights. In a DSPy program, the output of the optimization are the prompts. So you store the prompts and then you can reuse in an optimized program. So let me, and those are really nice examples here of how far can a DSPy optimization go, and it actually resembles a lot on what we human prompt engineers would do as well. Of course, because it kind of also learn from us, it's still an LLM behind the scenes, try to write those best prompts. So this is the classic example of separating the flowers by the sepal, the petal, and all those numbers. The classic machine learning problem. It's actually a terrible problem to give an LLM, but still, let's try. So starting with the most basic prompt, giving the petal and sepal dimensions, predict the iris species. So you see it achieves a score of 34. Now it changed a little bit and then it went a bit worse and then it kept trying. But the cool thing is that you can see the one that got the highest score was given the critical situation, which a rare species of iris is on the brink of extinction, predict the iris species based on the dimensions of the petals and the sepals in order to save it from extinction. So pretty catastrophic, but this actually gave way better result of 45. And we all know that when we add all those strong emotions to the machine, it tends to work better. It also finds that. The difference now is that you have a number to give it. You actually know how much better that is. And you don't need to be the one finding those best prompts yourself. You can let the machine doing. And then if you inspect it closely, the prompts might be a bit crazy like this, but hey, it works, right? So let me go to a bit of example that I have saved up here to build the classic array. So this is the main example also on DSPy, and we're going to use language visualizer to see the optimization happening and inspect it closely. What exactly is this DSPy optimizer doing? So first of all, I install the dependencies, of course, and then I need to prepare what LLM and retriever it's going to use for our RAG 2. That's easy enough. So you just set up an LLM. In this case, I'm using OpenAI. I'm just going to run to test it out. I have just a hello there and then it replies. So my LLM works. And then as the retrieval, I'm using Cobert v2. So Cobert is like a vector database. It's also created by Omar. But it's a very interesting one. I recommend you to search about it. as later as well, because it works a bit different. It keeps the performance of an LLM, you know, close to if you had it in context. So yeah, it has really an advantage in quality there over traditional vector databases. It's a bit experimental still, but yeah, it's very cool. But anyway, so this retrieval is it retrieves some Wikipedia articles, and I'm configuring here DSPy to use those two. So I'm going to use GPT 3.5, and I'm going to use Colbert as my retrieval mechanism. And then the dataset we're going to use for this problem is the Hotpot QA dataset. Now this is a very interesting dataset because it's about multi-hop questions. So this is those are questions that require you to do like an extra hop to get the information. So for example, there was a question about who is the what's the nationality of the chef in Mission Impossible movie. So you first need to look up the movie, and then you figure out who the chef was on that movie, and then you can answer the question. So those are really great questions because they kind of throw the LLM off a little bit, you know. So it kind of forces it to not just get the information from its own brain, but to look it up indeed on Wikipedia. Otherwise, it can be wrong a lot. So here we have 32 train set examples. So if I run this, yeah, so we get 32 examples for a train set, and then 50 more for dev set. So this is basically for us to train it and then evaluate the accuracy in a different one. I'm getting just a small sample amount to be faster to run the training examples. This dataset has more. But the interesting thing about DSPy is that since it's all LLMs, right, it doesn't, not all LLMs, but I mean, we are dealing at a higher level here, so it doesn't need that much example. It doesn't need 7 terabytes of examples, right? Like in if you're training a foundational model from scratch. So then, now that we have everything set up, we can actually start on the interesting part, which is defining our DSPy program. So your DSPy program is defined in modules. And this part is really cool because it resembles a lot PyTorch. So if you ever use PyTorch, you really feel at home here. But also, even comparing to other LLM frameworks, this is actually very easy. So when you, let's start with our main program, right? The one that starts everything. It's the rag, we just define a name here. And then we define 2 other blocks. So going back to our architecture, we are not going to do this generate query part. Just for simplicity, we are going to take the user input and we're going to put directly on the retriever. So we're just going to retrieve and generate answer, right? To have just two blocks. So the retriever is a simple DSPy retrieve. It works out of the box because it already knows that it's connected to Colbert. And then for generating the answer, we are going to use a chain of thought on top of this generated answer module. So I'll get that in a bit, but first, the generate answer module is defined as such. It's something that has context, that has a question, and then it gives out an answer. So the context is something that will be retrieved from the retriever, and the question from the user. So those are both input fields. So they require data to be here, and then to be given to it. And then the answer is an output field, because of course, given those, we want to generate an answer. Now you might see those strings. Those are, together with the names also count. Those are little hints for the LLM. So the LLM, we use the name context to understand that this is supposed to be a context. If you call it blue, it might mislead it a little bit. However, you don't need to worry about it too much. It's literally like just write whatever, like may contain relevant facts. You don't need to prompt engineer this because the whole point is that DSPy will do it for you. So this is like just something to start it up, you know? So yeah, this is all it needs. This is all it takes to generate an answer. What are the input fields and what are the output fields? So then on our DSPy module, we define the forward pass. And this is, again, if you come from PyTorch, this should be pretty clear, but this is basically what will happen once your module is actually called. So you call here, then what you're going to do, we call the retriever, from the retriever we go generate answer, and then we get the output. I like it a lot that it's just simple Python code. It is just written in this way exactly as I mentioned. So the context is just calling the retriever with this question and then taking the passage back. This is something that returned from the database. And then we call the prediction, which is generating answer given this context and this question. So we're just taking this variable and put it here. It cannot be simpler than that. And then we just return it. That's it. That's our prediction. We returned, we predicted this context and this answer. Cool. So this is already a fully functional program. So even without training it, even without optimizing it, you can already run it. So what I'm going to do here is take an example from the dev set, this random example 48, and then print the question, the answer. And it also has some gold titles that like the best Wikipedia titles that would reply to this answer. And then I can already make a prediction, and the way it's going to make a prediction is basically using this poorly written prompts. So if I run it, and this is the kind of question that I mentioned, like Susanna acted as film loosely based in book by who? By Danny Wallace. But then the LLM at first glance, like GPT 3.5, thought it was Clarice Lispector. Because to answer this, first you need to research on like which films did Susanna actually acted on, and it's not like yeah, everybody knows all the films, so it's unlikely to be there in the foundational model already written. So it has to do this RAG to answer it properly. And without training, without examples, it didn't work that well. So cool. So now we're going to go to the real exciting part of optimizing it. Let's go. First of all, to be able to visualize what optimization is doing, I'm going to log into LangWatch, so then we can visualize our optimization. How is it going, and what examples are trying, how much is it costing, etc. So the way we train it, the way we optimize it is first, now we have these examples. If you remember, we have our examples here, we have our architecture defined. Now the only thing that is left is defining our evaluation. So how do we know that our result was correct? How do we know that should be Danny Wallace, not Clarice Lispector? So we define a validation metric. In this case, it's a very simple validation. We are going to do an exact match and a passage match. We need to see if they both match. So it's basically a Boolean evaluator. It's either 1 or 0. It's correct or it's not. Because this is a very, let's say, well-defined problem as well. But you can literally put any Python code here, so you could potentially even call another LLM. You can ask the human to validate. You can go crazy here. Anyway, so as a first step, we're going to start as a simple optimizer. We are going to use the bootstrap few shot with random search optimizer. What does that mean? So remember then I said that one of the things that is very powerful is giving it few shot prompting, which is to give some examples like, hey, giving this and this question, you should answer it in that way. We can do that very easily on DSPy by simply wrapping around our module with few shot prompt. Oh, sorry, in this case it's chain of thought. Yeah, okay, sorry. Here we're not using few shot, we're using chain of thought. So chain of thought is before you give the answer, give it a reasoning as well. So you have the input, you have the context, then you think of a reasoning, you write a reasoning line, and then you give the example. You get the context, you get the question, you get the context retrieved from it, then you write a line of reasoning, and then only then you get you give the response. And the thing is, if you look at our data set, let me take an example from the data set. Yeah, if you look at our data set, you have question, you have answer, you have gold titles, but you don't have this reasoning. you have to generate this reasoning. So what the bootstrap does in the optimization is bootstrap some reasoning thinking. So it will give some examples, some demonstrations to the prompt on the LLM. So like the Clarice Lispector one, for example, it takes this example and then you should think it's the reasoning is this, and that's why the answer is that. But knowing the answer. So then the model that knows the answer will help the model that don't know the answer. So of course, for training it, we give it the train set, but then we evaluate on the dev set on data that it never seen. So it cannot get spoilers, it cannot get hints on data that it never seen. So it can effectively measure quality on unseen data. Let's just start with it, and then you see how it goes. So I have, so I started running it. I can click this link and then I can see how's it going. This one should be fairly quick, but it's running the examples here. The first 5 steps were already cached, so they were a bit faster. But anyway, if you look at what the optimizer is doing, first of all, it's trying with that simple prompt that we gave. This optimizer is actually not changing prompts, it's just changing the optimization. That's what the few shot here means, changing the demonstration, sorry. So first, just to have a baseline, it tries with no demonstrations whatsoever. And then there, the score is 31% accuracy. Can we increase this accuracy by giving demonstrations? So it gives some random demonstrations, and you can see those here. How old the fossil record, what person. And then what it does is taking those, and same in first step, and run through those 32 examples. So you can see like the first example, it was wrong. Like the model predicted, the correct one would be John Toes, and here predict Toes from Xanthus. You could say it's correct, but not according to our metric. It should be exactly correct, right? So that's a 0. And then in this one, it predicted Rodario Dawson, that's correct, and that's a 1. And then by taking all those and summing up an average, then you get the score of 34%. Then the optimizer keeps trying. What if we try different examples? And then here it gives some other examples. Let me get here which examples it got. So this one was like, which magazine published articles by Scott Shaw? But then apparently what gave us the best result, 40% accuracy, was those examples which start which American actress made on the film 1995. Yeah. Why did it work best? I don't know. But doesn't matter. It worked best. It produced best results, right? And then, because this is very interesting, this is the part that helps a lot, is the rationale. So this rationale is likely to help the data on the unseen data as well, because maybe it's better rationale examples, right? And this is the bootstrap part of the optimizer. Our original data set has no rationale, so it is taking some examples and then like, okay, how can you connect this question, this context to this answer? Produce a rationale to give it as example later and make the model that is running this smarter. Cool, so we got some nice results. Seems like we cannot go over 40. You can see that this training session cost us 50 cents. And this is something to watch out for when you're doing DSPy. Here we're using very little examples, and we are just testing on 35, 45. So you can see also the LLM calls that happen here and the cost of each, and you're using GPT 3.5. So be careful, otherwise your cost can explode, right? And this is the initial optimizer that you can try. Very, very simple, very easy to use. But the thing is that now you have a compiled RAG example, an optimized RAG. You first start, and you can see here the baseline was 31% score. So if you haven't done anything, then you get 31% accuracy on your RAG. But now that you run through the DSPy optimizer, you got it up to 40%, and that's really cool. You have a better RAG now, and you didn't have to find those best examples that make it work, or the best rationales that make it work. You let the optimizer do it for you. What you can do now is simply save it. So this will save it your compiled reg as a JSON, and like I said, instead of saving the weights like machine learning model, you save the prompts. We can even inspect it here later, I hope. Yeah, I actually don't know where it's stored, so never mind, but it's somewhere around there. But if you open, it's a very simple JSON file to read. It's more or less what's really written this. It says which instruction used, what context were used, yeah, the rationales used, and so on. Anyway, so now let's go more advanced. Let's go to Mipro. So this is the most powerful optimizer for DSPy right now. Actually, there is Mipro V2 yet. I haven't had time to test it yet, but yeah, I recommend that you do. But anyway, with Mipro, it not only optimizes the examples given, it does that while also optimizing the main prompt that's being used. And you can also optimize the signatures of the field. So here it says that the context field may contain relevant facts, the question field is just named question, but what if instead of question it was query? I don't know, would that improve the response? What if you see reasoning, let's think it step by step. What if it was, let's think very carefully, would it improve the scores? I don't know. So you can also use the signature optimizer, but right now we are going to use just the prompt optimizer together with demonstrations that Mipro does. And the cool part is that, remember that we're using GPT 3.5, right, to do these predictions, but we can use GPT-4 as a teacher. So I set it here as a teacher and also as the prompt model. So we have GPT-4 writing prompts for GPT 3.5. It's, you know, it's a more junior friend. And then it can give also, it can also behave as a teacher giving those reasonings, and then it can give amazing reasonings to GPT 3.5, basically saying like, hey, GPT 3.5, this is how you should think, right? And this itself already increases the quality while you're still paying for a cheaper and faster model. So yeah, let's start with this as well and just see how it goes. You see, like I said, on the cost thingy, that DSPy gives you a huge warning here, like, are you sure you want to run this? But yes, we are sure. Let's go here. Yeah, I once spent $30 on just like my first attempt, and then boom, it was like in a minute, my OpenAI credits were gone. But yeah, it happens, it's part of science. Anyway, so I have it cached already, so that's why it's going really fast. I ran it before to speed up the video, but then here we can see what's happening. Again, it started as 31%, but you can see already trying different prompts and demonstrations. So remember, our basic instruction was like this, answer, and then it tried this huge ass prompt to see what score it will get to that. And then it tried once more again. So it tries the same prompt with different demonstrations. Oh, this one with no demonstration. So look, this prompt with a few demonstrations got 31% score. This prompt with no demonstrations got 21% score. It was horrible, actually. So then the optimizer thought like, okay, maybe this is not a good direction to go, and then it goes trying other stuff. If I recall correctly, I configured it to try 10 different prompts. So yeah, here's another prompt, and then the score were more or less the same, but here you got a higher score of 37, and then all the way here, interestingly, it seems like 40% is the best we can get with this data set. But the other interesting thing is that apparently the best prompt was actually the simplest one. So sometimes huge ass prompts are better, but other times they're not. And then I find out with those demonstrations, now with the code for German offensive, then it actually produced the best result so far. And then we stopped there, around stopped there at 40. And then let's actually see the LLM calls that were done. If you look at the very first step, you can see that 127 LLM calls were done, and like they go really fast, 144,000 tokens. You can put them to run in many threads, so they run everything same time. So be careful also with your rate limits. But then you can see here that there was some calls to GPT-4 to generate those prompts and to generate those reasonings, right? to be later on used by GPT 3.5 to evaluate the scores and the results. And then you can track the cost of all that. This one costs 170. You can track the cost of all that. And yeah, so you can keep experimenting with it and optimizing it. So yeah, that was it. I hope that was interesting. That was as exciting for you as it is for me. I really think we're just at the beginning of this thing, but it's really a promising way forward. For one, I'm really, let's say, relieved to actually have a number attached to it, to actually have control, to actually see like, yeah, like it's really improving. Those prompts are really improving the performance, and to have something that can do it for me, so then I can just think about more meta level again, more architecturally. And then yeah, that's it. So if you want to try it out, I'll leave the link to this Jupyter notebook on the description below. And also, if you are interested, we are building a new solution to allow you to do DSPy in an interface. So instead of just doing through the Python, you'll be able to drag those components and modules and connect them together, and then with the button already run the optimizer and see how it goes. So if you're interested in something like that, I'm going to drop a link to a Google form below in the description. Please drop your name and your email there. We really want to reach out and then see what you think of it, collaborate together with you. Also follow me on Twitter. So if you're interested in more DSPy stuff, I'm going to continue tweeting about it. And yeah, thank you very much. See you there.